In this lesson, we will take a look at the geometry of the solutions of the homogeneous equation ax equals 0 and the non-homogeneous equation ax equals b in R3 with one free variable. Notice we are given matrix A and vector b below. Let's first solve the equation a times vector x equals the 0 vector. To do this, we set up the matrix equation where we have matrix A times vector x as a column matrix where the entries are x1, x2, and x3 equals on the right. We have a 3 by 1 0 matrix. The next step is to write the augmented matrix where the first row is 2, 2, 4, 0. The second row is negative 4, negative 4, negative 8, 0. And the third row is 0, negative 3, 6, 0. Then we write the augmented matrix in reduced row echelon form, which I've already done here to save time. Notice we have a pivot in row 1, column 1, and row 2, column 2, indicating x sub 1 and x sub 2 are basic variables. We have no pivot in column 3, x sub 3 is a free variable. The first row indicates that x sub 1 plus 4x sub 3 equals 0. The second row indicates x sub 2 minus 2x sub 3 equals 0. And because x sub 3 is a free variable, we have x sub 3 equals x sub 3. Next, we solve the first equation for x sub 1. X sub 1 equals negative 4x sub 3. And then we solve the second equation for x sub 2. X sub 2 equals 2x sub 3. Next, we can parameterize the solution by letting x sub 3 equal s, where s is any real number, giving us x sub 1 equals negative 4s, x sub 2 equals 2s, and x sub 3 equals s. Which means the solutions to the homogeneous equation are all the vectors x, where x sub 1 equals negative 4s, x sub 2 equals 2s, and x sub 3 equals s. Factoring out the s, we have vector x equals s times the vector negative 4, 2, 1. Which means the solutions to the homogeneous equation are all the vectors x that are scalar multiples of the vector negative 4, 2, 1. Let's take a look at this graphically. Here we see the graph of the vector negative 4, 2, 1. This is the solution when s is equal to 1, but this is just one solution. The solutions are all scalar multiples of this vector. We can also think of the solutions as points, where the points would be the terminal points of the scalar multiples of the vector negative 4, 2, 1. And now let's take a look at scalar multiples of this vector, which again are all solutions to the homogeneous equation. Notice all these vectors or all these points fall on the same line, which would be this red line here, and notice how the red line does pass through the origin. So we can say the solutions to the homogeneous equation are all the vectors or all the points on this line, which again is a line passing through the origin. The reason the line passes through the origin is because when s is equal to 0, notice x is equal to the 0 vector. And now let's solve the corresponding non-homogeneous equation where vector b is the vector negative 8, 16, 18. The process is the same. We set up the augmented matrix and then write the augmented matrix in reduced row echelon form. But notice now the fourth column is not a column of zeros. The first row indicates x sub 1 plus 4x sub 3 equals 2. The second row indicates x sub 2 minus 2x sub 3 equals negative 6. And again, x sub 3 is still a free variable. X sub 3 equals x sub 3. Next, we solve the first equation for x sub 1 and the second equation for x sub 2. And then to parameterize the solution, we can let x sub 3 equal t, where t is any real number, and therefore x sub 1 equals 2 minus 4t, x sub 2 equals negative 6 plus 2t. Which means the solutions to the non-homogeneous equation are all the vectors x, where x sub 1 equals 2 minus 4t, x sub 2 equals negative 6 plus 2t, and x sub 3 equals t. We can write this as a sum where we have the constant vector 2, negative 6, 0 plus t times the vector negative 4, 2, 1. So the solutions to the non-homogeneous equation are the vectors x, where we have the constant vector plus scalar multiples of the vector negative 4, 2, 1. Notice the only difference between these solutions for the two corresponding equations is that the non-homogeneous solution has this constant vector. Let's take a look at the solutions to the non-homogeneous equation graphically. To do this, we will first graph the constant vector 2, negative 6, 0, and then we'll plot scalar multiples of the vector negative 4, 2, 1, where we plot these vectors with the initial point at the terminal point of the constant vector. So this blue vector is the graph of the constant vector 2, negative 6, 0. And because we are adding scalar multiples of the vector negative 4, 2, 1 to this vector to find solutions, we will plot the scalar multiples with the initial point at the terminal point of this constant vector. So here I've graphed the vector negative 2, 4, 1 with the initial point at the terminal point of the constant vector 2, negative 6, 0. So the terminal point of this second vector represents a solution to the non-homogeneous system. But this is just one solution when t is equal to 1. So now let's graph scalar multiples of the vector negative 4, 2, 1 with the initial point at the terminal point of the constant vector 2, negative 6, 0. So all the terminal points of this second vector in blue represent solutions to the non-homogeneous system. And notice how all the points do fall on a line that is parallel to the solutions to the non-homogeneous equation. The solutions to the non-homogeneous equation are all the points on this blue line. So again, notice how the two lines are parallel, but the line that represents the solutions to the non-homogeneous equation does not pass through the origin. And that's because it's been shifted by the constant vector of 2, negative 6, 0. So we could say to find the solutions to the non-homogeneous equation, we would take the solutions to the homogeneous equation, the red line, and then shift them based upon the constant vector of 2, negative 6, 0. Let's go back and summarize our findings. For the homogeneous equation ax equals 0 in R3 with one free variable, the solution will always be a line passing through the origin. And the solutions to the equation ax equals b in R3 with one free variable will always be a line not passing through the origin. And if both solutions contain scalar multiples of the same vector, in this case the vector negative 4, 2, 1, then the two lines will be parallel. I hope you found this helpful.